this rather wonderful conference. I've really enjoyed my time here. And okay, so as was said, I will be talking about statistics and mechanics of Kirigami. I don't know if I'll be able to get to the statistics part, but at least let me try to do the mechanics. So this is, I'm going to be trying to summarize work done by a large group of people. Much of this work that I'll be talking about has been done along with Mikhail Moshe, who's over here, and with David Nelson in Harvard, and Mark Bowick at Syracuse. Okay, this works. And also, I will be talking a bit about, I will also be talking about some experiments done on paper in the lab of Itai Cohen. And so this is part of this graphene-DIMREF collaboration between Syracuse, Cornell, and Harvard. And some of this work was also done at KITP. So that's for the acknowledgments. Okay, so yesterday we heard about Kirigami and using Kirigami to make actuators from Marcello. And so the main interest, at least for me, in Kirigami is that you have a very nice technique which doesn't depend on the scale to be able to tune the mechanical properties by just changing the geometry of the material. So here is some patterns of slits done on the scale of centimeters in paper, and here demonstrated in graphene on the submicron scale by the group of Paul McQueen, by Melina Blees and the group of Paul McQueen at Cornell. And so you have great control over tuning mechanical features by just changing geometry. Oh, the other way. All right, and as we also heard yesterday, there's lots of people have worked on Kirigami and Kirigami Meta-materials in general. Many of the people are actually here in the audience, especially of this set of works. So you can, people have thought of designing systems with interesting mechanical properties like auxetic things, or you can, create 3D structures like Mount Katahdin using some lattice Kirigami patterns. And also actuators, and there's been lots of different kinds of work done on Kirigami patterns, but the general problem that given a pattern of Kirigami or holes or slits in a thin elastic sheet, to be able to predict or understand what the mechanical properties of such a material is going to be, that question continues to remain open. And the inverse problem of designing a particular Kirigami pattern to obtain a desired set of mechanical properties, that is also, it's not clear what the rules are to generally answer that question. And so, so some of the main challenges in addressing this question are that, as everyone over here already knows, that thin sheets are famous for their nonlinearity through the Foppel-von Karman, the Foppel-von Karman equations which govern their elasticity, and they're characterized by this dimensionless number, the von Karman number, which it's a ratio of stretching to bending, and this is huge for even things like paper. So basically, thin sheets don't like to stretch, and they only like to bend isometrically, and that introduces nonlinearity. The second point is specific to Kirigami, which is that in the presence of holes, like in a pattern like this, the inclusion of geometry into the mechanics is through boundary conditions, which are very non-trivial, to have stress-free boundary conditions enforced on the hole, and that encodes their particular geometry, and this affects the mechanics of the entire material. So we need to address both nonlinearity and non-trivial boundary conditions, and so our way ahead in answering these questions is basically to use a geometric approach of elastic charges to address both these points. And so in a way, I will try to offer the approach of elastic charges and actually image elastic charges as a sort of systematic approximation to the full mechanics of Kirigami, and perhaps it provides a fruitful way of thinking about Kirigami mechanics in general. But before going to the more complicated problem of an array of frames like this, which has couplings between holes and all sorts of complicated features, I will do the much simpler case, which is to go to a single frame, which is just here. This is a square frame. You can think of this as sort of a modular element out of which you can put many of these together to build a bigger lattice. And over here it's just square, but the ideas I will be talking about are general, so you can use them for other designs like circles or triangular holes or slits or more complicated patterns as well. So this is just an experimental picture from the picture of the experimental setup from Itai Cohen's lab. This is just to set the notation. So this is the frame width, the W. It will keep coming up later in my talk. Length of the square frame is L, H is the hole size, and the sort of setup we'll be thinking about is diagonally pulled frame. So I apply uniaxial tension, this is the force, and the displacement is basically delta x. For small enough displacements, the frame remains planar and it gets stretched, it's distorted, but beyond the buckling threshold, it buckles and adopts this sort of configurations. And so we're going to be interested in understanding both the mechanics and the deformation of this frame. And just to briefly tell you the idea of elastic charges and how it applies to Kirigami. Say we begin with a cartoon of two frames. So here's a square frame and that's an annulus. And I shall initially keep them planar. So I will be restricting the frame to remain planar. And as such, as drawn, these are stress-free and there's nothing happening, so it's rather boring. But now if I apply an external stress over here, shear, I pull along the diagonal, both frames, they deform. And by being planar, because these frames are planar, this sheet is stressed. And the elastic problem reduces to solving this sort of biharmonic equation, which is basically force balance, written in terms here of the Airy stress function in 2D. The important distinction from naive simple elasticity is for a regular simply connected sheet is that here the hole provides stress-free boundary conditions, which is what makes this problem complicated. But okay, in the plane for the circular frame, this is the solved solution of Michel, and you can actually exactly compute things. But there is an alternate way of viewing the same problem. Instead of imposing boundary conditions on this curve or here, one can instead, much like in electrostatics, instead of using boundary conditions, one can introduce a source term, here Gaussian curvature, which sources stresses. And this Gaussian curvature, which is basically the induced image charge, it's an elastic charge, is induced by virtue of the external load applied here, the sigma external, and this is induced within the hole. And so just like in electrostatics, when conducting shell kept in an external electric field develops induced charges to maintain the zero potential surface on the conducting shell. In the same fashion, the induced charges here, which in charges in Gaussian curvature, are created to maintain the zero stress-free condition on this whole boundary. And so there are some requirements on the form of this charge, this induced Gaussian curvature. So if you do a multipole expansion, the first and second term are not permitted. They're topological. That's the monopole and the dipole. They correspond to disclinations and dislocations. And the leading order term that is generally present is the quadrupole. So it has this minus minus plus plus fourfold symmetric pattern. And you can have higher order charges, but this is the often the dominant term. So you can reduce the problem of planar frames, with a hole to thinking about induced quadrupolar charges in response to external stresses. And so now if we ask, how well does this work? There's a small point. In the circular case, you can exactly solve this, and there's only two charges which are present because of circular symmetry. But in the square frame, all charges, including the quadrupole and higher, are present. But now, if you suppose for simplicity, truncate the multipolar expansion to leading order and just say that there is just a quadrupolar charge, and you compute what the planar effective spring constant under this loading condition is. So you pull along the diagonal and ask what the effective linear spring constant as a function of the whole geometry is in the plane. Here is in prediction the straight lines from analytics. The dots are from finite element simulation, and you get very, very good agreement without any fitting parameters. And also, if you look at sort of the deformation of the frame itself, if you can see the green dots, that's a numerical computation of the full nonlinear numerical computation of the frame under this load. And the red line is an analytical prediction, and they again look essentially, they'll lie on top of each other. And over here, you also see in the color map, the heat map, plot of the stretching energy, because the frame is planar. The stretching energy ends up getting localized. So you have stress focusing at the corners of the hole. And this is again reminiscent to the feature in electrostatics where charges, induced charges, get concentrated to sharp corners. And in much the same fashion, here the quadrupolar induced charge fractionalizes into partial disclinations, which leads to stress focusing at the corners. Yes. So I mean the what happens is, because we're replacing boundary conditions as a source term in the first Fopple-1 common equation, we know that once, what actually sources stretching is Gaussian curvature, and then we expand the Gaussian curvature to in multiples to, and then we know that the leading order of term has to be quadrupolar. So I'm not sure. I mean, this is fictitious Gaussian curvature. This isn't. I'm not sure I understand what stretches are present which don't induce Gaussian curvature. I don't understand that. Okay. So that's another. No, I think what you're okay. Yes, you're right. For this deformation, it's the quadrupole, which but there are other deformations. Okay, I understand that those are other pointer deformations, which exactly. Yeah, but there's also the point. No, but I think the point is, there's, apart from shear, there's also compression and isotropic compression and extension, which is another charge which I'm not mentioning. So but there's other charges also which one can include, but it's not relevant for what I have to say for now. Okay, so all right, so in the plane it seems to work all nice. You seem to be able to get both global measures of mechanics and even local deformations. It seems to capture quite accurately what one finds in numerics. So it seems to work as a good approximation of the elastic problem. But now if we relax the planarity condition and we allow the sheet to buckle, this is where we address the other complication, which is that thin sheets are nonlinear when you allow them to buckle. What happens is the first Fopple-1 common equation has an additional term, which is the actual Gaussian curvature of the sheet, which by virtue of its configuration, three-dimensional configuration that it adopts. And so one immediately sees that if the sheet buckles to adopt a configuration that screens or cancels out the induced image charge, then it permits the appearance, it makes accessible the zero stress state, which is the vanishing of the Airy stress function. And this is basically what thin sheets want to do. So they want to, so here you have the phenomenon of screening. So the sheet basically adopts that particular shape to buckle and to screen out the image quadrupole and be basically isometric or stretchless. And this is basically quite similar to the phenomenon of screening, which was discussed long ago by Sanger Nelson for topological disclinations. The only difference is now this is the same thing, but now done for non-topological quadrupolar charges. And so here is the buckled, finite element computation of a buckled square frame, a triangular frame, and a circular frame. The qualitative feature is that all of them, irrespective of the geometry of the whole, have this dominant quadrupolar symmetry in terms of the curvature localization. So this is basically the stress focusing that was there in the planar case now manifests itself as curvature localization at the corners. Over here, when the symmetry of the whole is not commensurate with that of the quadrupole, you have some bit of charge which is smeared smoothly, and over here all of the charge is smeared smoothly along the edge of the circular frame. So you have, which is why we chose the square frame to work with, because that's the simplest case where the quadrupole fractionalizes into partial disclinations. And so now the bent, the buckled frame can be rather easily thought of as a combination of locally conical surfaces that result from the buckling of partial disclinations. And so this allows us to simply easily compute the bending energy of this frame and its mechanics. Yes, Benny. So they're partial disclinations because it's much like the edge-supported econs of what is a partial disclination? Okay, I mean, it's in the sense that this angle when planar was 90 degrees, and if it deviates from, if it's smaller than 90 degrees, then it counts as a positive charge. If it's greater than 90 degrees, then it counts as a negative charge. And but it's not a real disclination in the sense that it's not topological. But exactly, yes, yeah. So I mean, because it's not the full cone. It's a section of a cone which has an starting angle. That's so in that sense. Okay. So this is how we gain access to the buckled frame by studying the planar frame, which is much simpler. Okay. So and one can do numerics again, and then have force response, force extension curves, and we see that for different, so these are for different frame width. So as you change the whole geometry, you can have even different buckling modes that may be favored depending on where you are in how much you've extended and what the force is and various things. And there's a more detailed comparison given in this preprint with numerics. But I want to switch and talk about the experiments. Which were done on paper frame. So this is sort of the experimental setup, and here's force extension curves for a given geometry. And basically what one has is, as one expects, you have pre-buckling, you have a linear regime which is dominated by stretching. So here we normalize by the thickness of the sheet, so that's basically dominated by planar stretching, and the sheet remains planar. Eventually, after this shoulder, you go to a softer plateau, which is dominated by bending, and so you have collapse here as you divide by t cubed, which is the post-buckling plateau. And so this is as expected. You have stretching, and then you have buckling to a soft regime of soft response. And now we can ask, what is the effect of mechanics in this post-buckled regime as a function of frame geometry? And that's what's here. So this is the in the buckled regime, in the post-buckled regime, we ask what is the effective spring constant of the frame, and as a function of the frame geometry. And so here, as a function of the frame width, so this is extremely, zero frame. The frame is non-existent. This is a narrow frame, and there you have the intermediate hole sizes. So these regimes of the frame width are actually, you can actually compute them naturally in the using quadrupoles. These numbers actually come out quite naturally. And the lines are basically analytical predictions, and the dots are the numerics, not the numerics, sorry, the experimental data. And you have, again, very good agreement. You also have, multi-scaling behavior. In this regime, the quadrupole is the most dominant charge, and so we can do computations. We're using, just the quadrupole here. more charges, higher order charges become important as the frame width becomes thin and it becomes more like a ribbon. And so we actually use a different approach to compute things. But in principle, we can capture all of these features as a function of all the geometric features. Also, the basic softening phenomenon seen in this side is the fact that the Young's modulus, the 2D Young's modulus, essentially gets replaced by the bending rigidity and divided by the frame width squared. And so this is the basic softening response post-buckling. And now we can, so that was mechanics. Now we can ask what about the buckling threshold. So this is, again, as expected. The dots are from the experiment, the straight lines, the theoretical prediction, the analytic prediction. So the threshold of buckling goes like t squared, where t is the thickness of the sheet of paper, and that's basically the balance between stretching and bending. Stretching is linear in t, bending is cubic in t, and so you balance the two and you get t squared. But the more interesting feature is here, which is the dependence of the buckling threshold on the frame geometry. So here's as a function of the frame width. The dots are the experiment again, and the line is analytical prediction. In this regime, where in this intermediate hole size regime, what one surprisingly finds is that wider frames, so this is the frame width, so wider frames actually buckle earlier. And this is a bit counterintuitive, at least to me, because narrower frames have lesser material, which I would have expected to buckle easier. But here it's actually the opposite, and this is a direct consequence of the fact that you have this curvature localization, which leads to partial disclinations, and the buckling of the frame is controlled by the buckling of partial disclinations. So that comes out quite nicely from both theory and is seen in the experiments. Okay, and so this was global. Global consequences of the Kirigami, of the geometry on the mechanics and the buckling. But we can do something we did before as well in the planar case, but now we can do it for the buckle case as well. What about local measures of deformation? So here's a map of the red lines are basically mesh drawn onto the undeformed frame, and we ask just after buckling, what does the frame look like? And here we just, by fitting a handful of scalar charges, so just scalar 5 or 6 numbers, we managed to capture quite nicely the full functional dependence of the full deformation field, the displacement of the entire shape of this frame just post buckling. So this way we even the quadrupoles also give a good description of the local deformation and not just the global mechanics. Okay, so this was basically the story for the single frame, and everything seems to work rather nice, but what about many holes, which is actually where Kirigami lies? And so one can do is, once you know what how to describe holes as basically containing induced charges when loaded, the charges capture the fact that holes act as sources of stresses or geometric incompatibility, and now we can use the interactions between charges to understand how many holes work. And one can actually show that if you pull a pattern like this, an array of holes in this direction, the quadrupoles align along the stresses, but the nearest neighbor interactions between quadrupoles here, it's repulsive, whereas in a pattern like this, the nearest neighbor interactions at 45 degrees is actually attractive. So an array of a Kirigami pattern like this will actually favor the formation of quadrupoles and thereby buckle favorably. And here instead it will be frustrated and stretch. And so you have a way of thinking about Kirigami mechanics in general as an array of charges with interactions. And so we can use this to ask how can we, so if you have an elastic sheet with some sort of pre-stress, can we design a particular Kirigami pattern that can relax that stress, and can we use interacting image charges to provide us a guiding principle to design a particular Kirigami pattern that would do this for us. And so, as an example, just to illustrate this point, if you take a cone and flatten it, regular cone, then leaving a small gap, the fact that this is not, this has Gaussian curvature because it at the apex, this is not when forced to be planar, it forms wrinkles, and wrinkling is one way of relaxing stresses for a thin sheet. But if you now put the appropriate Kirigami pattern that generates favorable quadrupoles that interact with the background stress, which would be present when the cone is flattened, then you can actually show that the radial Kirigami slits form favorable quadrupoles versus the azimuthal ones, where here the quadrupoles end up being frustrated, and this quite nicely relaxes the wrinkle state, and you actually manage to get the cone to flatten without wrinkling, whereas the azimuthal Kirigami pattern continues to wrinkle, and it doesn't, the slits don't help in relaxing the internal stresses. And so the main point is that elastic charges, and in particular with including interactions, can actually provide a useful way for thinking about the mechanics of Kirigami, and even perhaps designing Kirigami structures with specific mechanical responses, here in particular to relax pre-existing stresses. And I think I have, what, 2 minutes, 3 minutes? 2. Okay, so this is, so as I expected, I don't have enough time to talk about what happens now if we add thermal fluctuations. If you're interested in micron-sized graphene sheets with Kirigami done on them, then thermal fluctuations are important. And there's been lots of old work knowing that including thermal fluctuations, the bending rigidity renormalizes at large scales, and so there's and stabilizes the long-range order of the flat phase. And then one can ask, what is the effect of holes on the flat phase and crumpling transition? And because I'm out of time, I will perhaps just show a movie. Okay, so this is just to an illustration. So here is a molecular dynamics simulation of a perforated membrane and a flat membrane at the same parameters and at 3 different temperatures. And what's known for the intact membrane is that as you increase temperature, you have a flat phase to a crumpled phase crumpling transition driven by temperature. And what one finds is that including perforations or holes, you can actually tune the crumpling transition by a large fraction. So here's even when the intact membrane is well in the flat phase, you have the perforated membrane crumples much earlier. And so I don't think I have time to actually explain how we understand much of this. So, okay, so you get all of this. You can understand crumpling of thin frames as well using a renormalized persistence length that depends on the bending rigidity, and so some of the things that we're actually trying to do is to use the idea of interacting image charges to also understand the effects of thermal fluctuations in perforated sheets. And so with that, I will end and take questions. Thank you.